Okay. So, if not, the next concept that we are going to look at is what is called as a Nyquist stability criteria. Okay. So, yes. Yeah. So, do you agree that this transfer function is a minimum phase transfer function? So, as we know, as omega tends to infinity, the angle goes to, phase goes to minus 90 times n minus m. So, you substitute n and m, what do you get from this formula? 0. And then you go to the Nyquist plot. Where is the transfer function as omega tends to infinity? Plus 1. You draw a vector from 0 to 1. What is the angle made with the vector? 0 degrees, right? So, I am just using the Nyquist plot to just, if you draw the Bode plot, you will once again observe the same thing. I am just interpreting it from the Nyquist plot, that is all I am doing, right. Yeah. Okay. So, one important application of the Nyquist plot is what is it, to figure out the stability of the closed loop system, right. So, so if you recall our notion, our block diagram, you know, like of the closed loop system that we have been looking at, is that like the forward path transfer function was g of s, if you recall. Okay. So, this is e of s, right, and this is y of s, and the feedback path transfer function is going to be h of s, and this is going to close the loop. Let us say we have negative feedback, let me call the signal as w of s, right. So, this is the block diagram we have. What is the closed loop transfer function? Recall that y of s divided by r of s is going to be equal to g of s divided by 1 plus g of s h of s, right. So, this is the closed loop transfer function. Okay. Okay. So, now how do we once again like determine whether the closed loop system is stable? See, I am only asking the same questions again, right, we are revisiting the same points, right. How do we check out the stability of the closed loop system? We look at the closed loop characteristic equation. So, the roots of this equation are the closed loop pole, right. So, this is the closed loop characteristic equation. Okay. And you immediately see that the closed loop characteristic polynomial is going to be equal to 1 plus g of s times h of s. Okay. That is what we have, right. That is the closed loop characteristic polynomial, right. So, let g of s times h of s be NOS divided by DOS. So, I am using the subscript O to indicate that that is the open loop transfer functions numerator and denominator. See, in general we write any transfer function as a ratio of two polynomials in S, numerator polynomial n of s and denominator polynomial d of s, right. That is what we have been doing, right. So, I am just saying it as NO of s divided by DO of s, right. So, that is what we have. Okay. So, this implies that 1 plus g of s h of s is going to be equal to 1 plus NO of s divided by DO of s, which is nothing but DO of s divided by NO of s divided by DO of s. Okay. So, we will see why I am doing all these things. Okay. So, because I want to set some terminology in order before we go further, right. So, this immediately tells me that you can immediately see that the poles of 1 plus g of s h of s are, what are they? So, if you consider the closed loop characteristic polynomial 1 plus g of s h of s, right, that is going to be a ratio of two polynomials in S, is it not? This is also a ratio of two polynomials in S. What is the denominator polynomial? dO of S. What are the roots of dO of S called as? Poles of what? Open loop poles. Please remember that, okay, because dO of S is the what to say, the denominator polynomial of the open loop transfer function. So, immediately you see that the poles of 1 plus g of s h of s are the open loop poles. Are these known in general? By and large they are under our control, right, because what do the open loop poles constitute? They constitute the, what to say, the plant poles, controller transfer function pole and the feedback path transfer function pole. So, in general at least we will be able to tune them, even if the controller contributes some open loop poles, we will be able to tune them. So, we know what these poles are, right, yeah. So, what can you say about the zeros of 1 plus g of s h of s? What are the zeros of the polynomial closed loop characteristic polynomial 1 plus g of s h of s called as? We have already discussed this, I am just recapping. Closed loop poles, that is it, right. So, yeah. So, I am recapping this terminology once again because we are going to mix poles and zeros, right, but I want us to be very clear, okay. I am considering the polynomial 1 plus g of s h of s, which is a ratio of two polynomials. It so happens that the denominator polynomial of 1 plus g of s h of s is the same as the denominator polynomial of the open loop transfer function. So, the poles of 1 plus g of s h of s are nothing but the open loop poles. The zeros of 1 plus g of s h of s are the closed loop poles, okay. This is one which is of importance for us, right, because we are when we design the closed loop system, we are worried about the closed loop poles. Open loop poles are already given to us, right. We are worried about what are the closed loop poles. In other words, what are the zeros of 1 plus g of s h of s? Is it clear? Okay. Now, please remember this, what to say, terminology. We are going to pose a question. Yes, please. Why should they be closed loop zeros? No, but 1 plus g of s is the denominator of the closed loop transfer function, right? Isn't it? I am extracting, that is why I am doing it carefully, step by step, okay. So, please go back and of course, very natural question, because I am extracting the denominator, then I am writing the denominator of the closed loop transfer function as a ratio of another numerator denominator, then I am processing it, right. So, that is why I am doing it step by step, okay. But from here onwards I will just use this terminology, okay. That is why we came to this, right, okay. Now, the question that we are asking ourselves, we are going to ask ourselves, and the question, the answer to which would be provided by the Nyquist stability criteria is the following, okay. Given the open loop transfer function g of s times h of s, okay, that means we know the open loop poles, okay. Can we comment about the stability of the closed loop system using the Nyquist plot of the open loop transfer function G of s H of s. Okay. This is the question we are going to ask ourselves. Okay. So let me repeat the question. So let us read the question. That is, you are given the open loop transfer function G of s H of s, right? By and large, it is known, right? So we know the open loop poles, right? So open loop poles are nothing but the poles of 1 plus G of s H of s. Okay, please remember that, right? So as we see in the green box, right? So open loop poles are nothing but poles of 1 plus G of s H of s. We know them, right? Given the open loop transfer function, can we then use the Nyquist plot of the open loop transfer function G of s H of s to comment about this closed loop stability? Okay, that is what we are asking ourselves. Okay, and of course the answer is yes. That's why we have the Nyquist stability criteria. So, but the general result on which this stability criteria rests on is what is called as the mapping theorem. Okay, in complex algebra, there is something called as a mapping theorem. Okay, once again, I am not going to prove any of this. We are just going to use them. Okay, the mapping theorem leads to, of course, this is the answer. Of course, the answer is yes. Okay, how? You know, like we will visit what is called as a mapping theorem, and the mapping theorem leads to what is called as the Nyquist stability criteria. Okay. So this is what I have typed in that handout. Okay. So what I want you to do is that now I want you to read through the handout if you have not already done. So if you go to the course website, below root locus construction, I have uploaded another file called Nyquist stability criteria. I hope you are able to access that file, right? So in that I have clearly typed what is the mapping theorem and how it is applied to the Nyquist stability criteria. Kindly go through the document and come to the next class. We would discuss the same, right, in the next class. But I am going to leave you with another question. Okay, please think through these questions. Okay, let's say let the plot of G of j omega H of j omega, that is the open loop sinusoidal transfer function. Okay, so G of s H of s, you substitute s equals j omega, you get the open loop sinusoidal transfer function, and let this be given for omega belonging to 0 to infinity. Okay, so that's what we have plotted as a Nyquist plot, right? You give me any transfer function, that's a Nyquist plot. See, for example, let's say, just for sake of example, let us say the transfer function s plus 1 divided by s plus 10 was the open loop transfer function, let us say, right? We have plotted the Nyquist plot of that as omega varies from 0 to infinity. Okay, so till now we have been looking at omega as a physical parameter, right, where you know, like it is associated with frequency and it can take only positive values. But when we go to this mapping theorem and Nyquist stability criteria, we are going to look at omega as a real parameter, okay, and it can take values from minus infinity to plus infinity. Okay, we will learn that in the next class. So if that is the case, how can one obtain the plot of G of j omega H of j omega for omega between minus infinity to 0? Okay, so the Nyquist plot, you know, like by definition it is a plot of any transfer function by substituting s equals j omega, and you plot from omega going from 0 to infinity. That is the definition. Okay, but let us say let us now look at omega as a parameter, okay, rather than associating the meaning of frequency. Okay, so let us say I substitute s equals j omega. Omega is now a parameter, and that parameter can vary from let us say minus infinity to plus infinity. So, I am given already the Nyquist plot of the transfer function when omega varies from 0 to infinity. How can I get the Nyquist plot of the same transfer function when I go from minus infinity to 0? Okay. Please try this one out for all the transfer functions that we have plotted, okay, till now, and then like figure things out, right, what happens. So, let me do for one example, okay, and then of course, I am going to let you extrapolate, okay. So, I am just going to do one example and then we will see. See, for example, we did 1 by s, right, g of s was 1 by s. So, this means that it is essentially minus j by, g of j omega was 1 by j omega, right. So, this is minus j by omega. So, now if I have omega to be non-positive, that is it comes from minus infinity to 0, what do you think will happen? Let us plot. So, what was the Nyquist plot when it came from 0 to infinity? As it reached infinity, where did it go? We did it yesterday, right? The Nyquist plot was the negative real axis, imaginary axis. This was omega tending to 0. This is omega tending to infinity. Let us say it is the other way around. What will happen? When it goes from minus infinity to 0, what do you think will happen? What is the value as it tends to minus infinity? Anyway, it will be 0. And for as it goes to 0, it will blow off to plus infinity because it is coming from the negative side. So, what will happen is then it will also start from this as it goes from minus infinity and then it will go to plus. This is omega tending to 0 minus. So, I am just going to put a 0 plus and 0 minus just to indicate that from which side am I coming to 0, alright. 0 plus means I am going to 0 from the right, okay. 0 minus means I am coming to 0 from the left, from the negative real axis, right, negative side, okay. But of course, this is a very special example. So, you will see that you will have a what to say, radius of semicircle of infinite radius as your Nyquist plot, but this is a very special example, okay. I am just giving you one example to show you how to do that, right. So, kindly plot the first order factor that we looked at and then tell me what you will get, okay, when you have omega as a parameter which varies from minus infinity to plus infinity, okay. So, that is something which I am going to leave it to you as homework, fine. So, when we meet in the next class, we will look at the mapping theorem and then we will also discuss the Nyquist stability criteria, okay, yeah.